So we spent all this time learning what all the different menagerie of functions look like because we're starting to work with piecewise defined functions. So a function is called a piecewise defined function if it's defined by different equations over different intervals of its domain. So let's take a look, for example, at this image here. So from when x is -3 to when x is 1, right? This equation is defined by 3x plus 1. And it's not an equation, it's a function. So we have the equation 3x from when x is -3 to when x is 1. Then from when x is, well, this shouldn't have an equal sign here because it's just less than. We've got an open dot. That means that endpoint's not included. So I've got a less than. Then we have the function from when x is 1 to 3, we have the function y equals 4. So we just have that constant function 4 from when x is less than or equal to 1, less than or equal to 3. So on the interval from 1 to 3. Then we skip over a point. And we have when x is greater than or equal to 4, we've got a closed dot. My function is defined by x minus 4 squared minus 2, which is a parabola. So what we're doing in a piecewise function is we're taking our domain and we're breaking it up into segments. Now realizing that this should have just been an equal sign as well. A less than, a strictly less than, because this 4 was not included. Let's work through some examples. Sorry about the ambulance. You guys know how busy Grand is. So here I have a piecewise linear function. I have f of x equals 1/2 x plus 2 if x is greater than or equal to -2. And I have my function defined by -x minus 3 if x is less than or equal to -2. So what I like to do is I like to go ahead and divide up my domain. I know my domain is divided up in this case at -2. So here's where -1, -2. I just draw a nice little dashed line so I can see what's going on. So when x is greater than or equal to -2, that's going to be this side, right? This is the side where x is greater than or equal to -2. I'm defined by the function 1/2 x plus 2. So let's go ahead and graph this. My y-intercept is 2. My slope is a positive 1/2, so I go up 1 over 2. Now that I have 2 points, I can go ahead and graph my line. But we have to be careful as we approach where our domain is divided in 2. -2 is included in this section of the domain because it's greater than or equal to. So I'm going to use a solid dot. Now, when x is less than -2, my function is defined by -x minus 3. So I'm going to go ahead and graph this line. There are 2 ways I could do this. One, I could find a couple of y values. That's what I'm going to do because I don't want to confuse myself by going ahead and starting to graph it over here and then having to erase. So that's the way I prefer to do it, but it is entirely up to you. So I'm going to go ahead and pick 2 points. I'm going to pick when, let's graph this in orange. Let's say f of -2, so I know what's happening on at this point. And I also want to pick f of -3. So I have a -2 plus 3, minus 3, minus 3. That gives me 2 minus 3, which is a -1. And then at 3, I have a -3 minus 3, which gives me a 0. So I have when x is -2, y is -1, and that point's not included, so I'm going to use an open circle because it's a strictly less than. And then I have when x is -3, y is 0, and that makes sense, right? I always want to look at my slope. Okay, I'm supposed to have negative slope. If I connect these 2 points, I can see that my line has a negative slope. So the domain, this function was defined over the entire real number line. My range, if we want to look at our y values, right? My range goes from -1, but -1's not included. So we're going to give it a parenthesis, all the way up until infinity. What are my intercepts? Well, my intercepts are, my y-intercept is when x is 0, y is 2. So that's my y-intercept, is when x is 0, y is 2, and I'm going to write it as an ordered pair. And my x-intercept is when y is 0, x is -3. Let's take a look at another example. Here I have an absolute value function and a quadratic function. So I have the absolute value of x is defined if x is greater than -2. So let's go to where we've got -2. So if x is greater than -2, I've got the absolute value of x. So that'd be on this side. I've got the absolute value of x. And then I have x squared minus 2 if x is less than or equal to 2. Okay, that should be a -2, less than or equal to -2. So that's going to be over here, x squared minus 2. That's where my function is defined. So I'm going to go ahead and graph the absolute value function. That's going to match every element in my domain with its distance from the origin. I know that -2 is not included because it's a strictly greater than. So here would be our absolute value function. Very pretty, I know. Now I've got x squared minus 2. So I'm going to go ahead and pick some values. I'm going to pick -2. And I'm going to go ahead and pick -3. I wonder if I'll be able to fit these on my graph. -2. Yep, we'll use black. That's fine. And -3. So I have -2 squared minus 2. That's 4 minus 2, which is 2. Cool. I have -3 squared minus 2. That's 9 minus 2, which is 7. So I have when x is -2, y is 2. And that point's included on my graph, so I can fill that in. And I have when x is -3, y is 7, 3, 4, 5, 6, 7. So there we go. And this is a parabola, so it's going to kind of have a little curvy shape. What's interesting to see is that where we had a gap left by our absolute value function, our quadratic function filled in. So our domain is all real numbers, and our range goes from 0 to positive infinity, and our x and y intercept are the same point, and that's our origin, which is the point 0, 0. So our last piecewise defined example is f of x equals x squared when x is greater than 0. F of x is 2, which is a constant function, when x is between 0 and 3. And f of x is 4 minus x when x is greater than 3. So this actually divides my domain up into 3 sections. So I have when x is greater than when x is less than 0. That's right here. This is where x is less than 0. I have when x is between 0 and 3. That's right here. 0 is less than equal to x less than equal to 3. And I have when x is greater than 3. I have this defined by 3 different functions. So I'm going to start by graphing my quadratic function. I have x squared. I know that 0 is not included, so it gets an open spot. 0, 0, 0 squared is 0. -1 squared is 1. 2 squared is 4. So here we've got our little quadratic graphed so beautifully. Next, my function is defined at f of x is equals 2 when it's between 0 and 3. 0 and 3 are included, so I'm going to use closed dots so that I know those points are in my solution. And then I have 4 minus x. That should give everybody kind of the heebie-jeebies. Like, ooh, why is it written like that? I don't know why I just oohed so loud. Okay, it actually should be -x plus 4, right? We typically always want our variable first. Now we are in slope-intercept form, y equals mx plus b. So I know my y-intercept is 4 and my slope is -1. But here's the issue. My y-intercept, that y-axis isn't in the part of the domain where this function's defined. So I'm going to pick a couple values. I'm going to pick f of 3, which isn't included, but it's an open dot and that's okay, and f of 4. So f of 3 equals negative 3 plus 4, which is 1. F of 4 equals negative 4 plus 4, which is 0. So when my function, when my x value is 3, my function value is, my y value is 1, and that point's not included. And when my x value is 4, my y value is 0, and I've got a negative slope, which makes sense. Okay, what is my domain? Well, this is defined over all real numbers, so it's from negative infinity to positive infinity. I can also look for my range, right? I know that this function is going to continue on down forever, so my range is actually all real numbers again, which is very nice. My x-intercept is here, so that's when x is 4, y is 0. And my y-intercept is here, not here, just here, and that's when x is 0, y is 2. So that was our final example for a piecewise function. I think the best way to start out is kind of by breaking up your domain, like I did over here on the right, and that should help you out.